1, 1, and 0, I want to be sure that this vector will be mapped into the 0 after the image. So this is in the main domain. Once you do the function or the transform, it should be mapped into a 0. The G function is not supported. This is what I'm telling you about. So if I have f like this, I will take this vector and make the substitution and the check, but unfortunately it's not here. So all I have to do now is to get advantage of the matrix of the coordinate change from B into B dash. This is the matrix controlling this linear transform, which is 1, 0, negative 2, and so on. Now, I will try to check for the vectors 1, 1, and 0. So I will have to get the coordinates of 1, 1, and 0. Simple. This is V, which is given to us by 1, 1, and 0. x1 times B, x2 times x1, x2, x3, those are the coordinates with respect to basis number B. I will equate the values. So if you start equating the values, you will have x1 equal to 1, x2 equal to 2, and x3 equal to 0. I will take all of this as a given in the next slide in order to be able to solve it. So the coordinates mainly are 1, half, and 0. So once more, the coordinates are 1, half, and 0. I'm sorry, 1, half, and 0. Now, all I have to do is to multiply these values of the coordinates into the matrix of the coordinate change in order to get the corresponding values, but with respect to B dash. This is done, which is half, 0, and negative 1. So actually, I'm multiplying the matrix of the coordinate change in the coordinates with respect to beta to get the coordinates with respect to B dash. Now, to the point, the critical point. If we use these coordinates on B dash and the result is the origin, okay, then this is going to be a kernel, belongs to the kernel. If not, it's not going to be. So all I have to do now to get the G of 1, 1, and 0, which is 0.5, the first component, times 0, 0, and 2. This is for B dash. Then I will take 0 times negative 1, double 0. And then the last coordinate, which is negative 1, times 0, 1, and 0, as you can see. The result is 0, negative 1, and 1, which is not, of course, what's given. So the 1, 1, and 0, therefore, doesn't belong to the kernel of G. And so number D is not correct. The last thing is he's giving you a set and he's asking you if it is a generating set for the image of F. In order to check that the set of these two vectors is a generating set or spans an image of F, all I have to do is to compare the results that I have with the values that I have from the image. So actually, this is XYZ belongs to R3. The X component should be A minus B minus C, Y A plus B plus C, and Z as 2A from the definition of the F function. Let's check the standard basis of R3, which is the canonical basis. Let's see if they are contained in this function. So this is 1, 0, 0. I will get the image of the canonical basis of R3, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. Taking these values, entering them in the function, I will get the images which are 1, 1, 2, negative 1, 1, and 0, negative 1, 1, and 0. The set of these components, the first two components, are actually what's given. So yes, it spans the image perfectly. So the first two components, the distinct vectors, are actually in the set that spans the image, which is correct. As you can see, don't get afraid from answering these questions. Step by step, do it easily, it will be run smoothly. Here, as I told you, we started from the function, we got the image of this function, we used the canonical basis, and they made the substitution in the F function to get the images. We can see that the images is already what's given, so you are in a very good shape. Okay, for question number 4, he's giving you, that's a good question. He's asking you about A which belongs to a square matrices such that A squared plus A equals 6i indicate the set of eigenvalues of A. Stop. Now, to get to the eigenvalues and the eigenvectors, I can get them from the definition and also I can get them from a normal problem. Here, he's giving you from the definition. The definition states that. What is the definition of an eigenvalue and eigenvector? The definition of an eigenvalue and eigenvector states that if I have A times V, it will equal to some scalar value, lambda times V. This is the statement. This is the definition of the eigenvector, which is V, and the eigenvalue, which is lambda, with respect to any matrix A. So all I have to do now is to check this. And we already have the solution here. So let's see how to check this. I will start from the definition, which is, from the given, which is A squared plus A equals 6r. I will multiply this by the definition of V. So I should have, in order to have an eigenvalues and eigenvector, this definition should be satisfied. So I will get the function V, or the vector V, which once we multiply by this value, we will have our result. A squared V plus AV equals 6 of V. So this is the main vectors that we are using. We already know that A times V should equal to lambda V if lambda is the eigenvalues. I will make a replacement. So now I can replace A times V by lambda V. Now I have a value for an eigenvalue to search for. Same way like for A squared V, it can be an A times AV, and A times AV. Now I can replace AV by lambda V, exactly like this. Now I can take lambda is a scalar value, A is a matrix, and V is a vector. So I can take lambda outside. I will have also A times V, as you can see, which can be really replaced also from the definition by lambda V. So it's going to be lambda squared V. Now I'm dealing with a quadratic equation. Lambda squared V plus lambda V equal to 6 of V. Divide on V or remove V from both sides. I will have an equation in the eigenvalues. Solving this equation will develop the values of the eigenvalues for this condition, which is lambda equal to 2 and the lambda equal to -3. This is why G is the correct answer. This treatment of finding eigenvalues and the eigenvectors, the eigenvalues, here you can find the eigenvalues, but it's difficult to find the eigenvector. It's very new. So all I had to do is to take just only the statement, the given. Once more, I'm taking advantage of the definition of the eigenvalue and the eigenvector. Trying to multiply this by the eigenvector and making a series of substitutions. So this is the given, which is A squared A plus 6i. I will multiply by a vector, which is the eigenvector. Now it's going to be like this. I will start taking advantage from this knowledge or from this part of the definition of the main definition. I will remove AV instead by lambda V, so I will have A squared V plus lambda V equal to 6V. Then I will continue. This is going to be easy. A squared V, I need to insert the eigenvalues once more. So take A as a common, consider A and V, make the replacement once more. Reorder that matrix times a times a scalar value times a vector. So rearrange them, getting lambda outside. So you will have A times V. Okay. Now once more make the replacement. AV, move it, and replace AV by lambda V. So you will have lambda squared V, which is really very simple. So now once more, I have lambda squared and V, as you can see. Make the replacement. Now the equation all in the only unknown, which is the eigenvalue. Take the divide on V and start analyzing lambda squared plus lambda equal to 6. And this is going to be lambda minus 2 times lambda plus 3 equal to 0. And it's really very simple to evaluate these values. It will develop the eigenvalues, as you can see. Okay, perfect. Now for question number 5. He is asking you, let R3 into R3, which is a linear transform, and another function, which is G, also moving from R3 into R3, be both linear transforms. Let B1, B2, and B3 arbitrary bases for R3. So it is, as we spoke previously about these problems, let's consider this is the main domain, this is the co-domain. So this is main, this is co-domain. That's R3, okay, because you are moving from R3 into R3. You have two functions here. This is function f, and that's function g, which is moving stuff between them. You will have B1, since R3 is R3, you will have B1, B2, B3, and also in R3 you have B1, B2, and B3. These are the bases that that was given to you. No definition, nothing. Is asking you about how to circulate all of this. He's asking you about G composite F, which means I will start from B3, mapping B3 into B1, and I want to check the indices. So once more, this is the results for this problem. I will start step by step. So let's start with comparing left-hand side and right-hand side. This is very, very simple. The left-hand side of number A states that the coordinates change matrix maps the basis of B3 into B1. So I'm mapping the element of B3 using the coordinates of B1. This is what is stated in here, B3 into B1. For the right-hand side, indicates that the coordinates change matrix maps the basis of B3 into coordinates in B2. So it starts with B3 into B2, then from B2 into B1. So this is the first matrix that maps B3 into B2, and then I will start mapping B2 into B1, and this is the matrix, the required matrix for the coordinate change from B2 into B1. Comparing these two, this is exactly as explained. I am making a transform from B3 into B2, then from B2 into B1, which takes exactly the image of making the composite from G into F from B3 into B1, which means that this statement is correct. So the first statement for sure is correct. The second statement is B is bijective, which means it's inversible. So I can go using F, and since this transform is bijective, I can get back. So I can map from B3 into B1, then I can make the inverse from B1 into B3 and vice versa. Okay, almost correct. The error in the order of the inverse coordinate change matrix. Let's see. Now, since F linear transform bijective, it means reversible, as I told you. Okay, F is bijective, and we are moving from B1 into B2. This is A. Once you start making the inverse, I will have F minus 1, and I will be moving from B2 into B1. This is very, very tricky. Need your focus on this. So the inverse matrix, it will be F minus 1, replacing the function that we have, and we will move back from B2 into B1. Unfortunately, if you try to compare the result with what's given, it's not correct from the indices. This is a mapping B2 into B1, but here B1 into B2, and this is why it's not correct. If I want to go for C, here's M from B1 into B2, which is A, and M from B3 into B1, and he's making an identity matrix of A times identity matrix of B2 to B1, and this circulation using the identity matrix is not right from the indices. I have wrote to you this statement doesn't hold in general. The transformation B3 introduces a basis change, but it doesn't simply wrap around A. I don't have to move around A. So moving A here is not correct. It's not going to give you the movement that you're in for, so it's not correct. For number D, for any basis, the ID transformed into the same basis, of course, will be the unit matrix, so number D is correct. For this statement, it's from the definition. If you have a kernel of F, intersection kernel of G, it's a subset from their addition. And this is actually true from the definition, as I told you, if V belongs to kernel of V and intersection with kernel of G, then f of V is equal to 0, the function will be mapped, that's the definition of the kernel. Same way like for the G of V, it's going to be mapped into 0. So f plus G acting on V, it's going to be equal to f of V plus G of V, 0 plus 0 equal to 0, which means that the kernel belongs to, that is a subset from the kernel of f plus G directly. This is for question number 5, which is correct, of course. For number 6, he is giving you, and this is somewhat easier question, because he is asking you about the eigenvalues and eigenvectors, as you can see. From A, he's giving you an A matrix, written A of alpha in the algebraic multiplicity, Mg in the geometrical multiplicity, as he stated, and alpha are the eigenvalues. 2 is an eigenvalue of A, so I need to evaluate the eigenvalues. And the eigenspace associated with the eigenvalue 2 is 0, 0, and C. I will have to check. So, bottom line now, I will need to get the eigenvalues and the eigenvectors in order to check number B. Number B, 1, 1, 1, is not an eigenvector of A. I will have to evaluate them. The matrix A is diagonalizable. Oh, stop. I will have to evaluate all of these. So I will start now with the evaluation of the eigenvalues of this matrix. So I will get my determinant, subtracting lambda or alpha from the principal diagonal. This is what we do. We took the matrix that's given, subtracting the eigenvalues from the principal diagonal, and putting all of this equal to 0. Now I will have to expand this determinant, which is going to reach to an equation, a third-degree equation. Solving it will develop the values of the eigenvalues. So I will multiply 4 minus alpha times negative 2 minus alpha times 2 minus alpha for the principal diagonal. Then I will have negative 1 times 2 times 0, which is 0. 0 times negative 4 times negative 1, which is 0. Minus 0 times negative 1 minus alpha times negative 1, so it's 0 also. 0 times negative 1 times 4 minus alpha, which is 0. Negative 4 times 2 minus alpha, which is going to develop a value. So now I will start expanding exactly as I told you. These are the principal diagonals. This is the remaining part. I can take 2 minus alpha as a common from this part and the second part, so it's going to be like this. I will try to expand this quadratic equation, which is going to be an 8, negative 2 alpha plus 4 alpha, which is 2 alpha, minus alpha squared. Then I will try to also to simplify things a little bit, so it's an 8 minus 8 is going to be 0. This is going to be minus 2 alpha plus alpha squared. And I will start to do the multiplication once more. So we ended up having an alpha, 2 minus alpha. Also, if multiplied in negative, so it's going to be 2 minus alpha also. That's the eigenvalues are alpha equal to 2, repeated 2 times, so algebraic multiplicity of 2 is 2. And alpha equal to 0, so the algebraic multiplicity of 0 is 1. Now I can answer the questions. Wait, he's stating here in C the matrix is diagonizable. Of course not diagonizable, because one of the eigenvalues equal to 0, so this is not correct. Also, let's see, if it's not diagonizable, then there exists an inverted matrix V minus 1. This is not correct. It's not going to be like that because it's not invertible. I'm sorry, it's not diagonalizable. So both C and D now are answered from this system. Now he is asking me about the eigenvectors. So I will start to get the corresponding eigenvectors of both 2 and 0. How to get the corresponding eigenvalue of a 2? I will solve this system replacing alpha by 2. And this is what I did here. Let alpha equal to 2. So I will take this system, inserting alpha equal to 2. This is the matrix that I will have. I need to put it on the reduced echelon, or as much as possible to reduce the iconic reduced echelon form. I will replace the third row instead of the first row and vice versa. And multiplying the third in a positive, so it's going to be 1, 1, 0. These are the two rows developed from this replacement. Then I will multiply by -2 and add on the second row and on the third row. We reach this form. So finally, it means that the first component equal to 0, the second component equal to 0, but the last component is equal to a constant. So the eigenvector here is going to be 0, 0, and C. As you can see, 0, 0, and C. This is U1 first component, as we used to write. First vector, second component. First vector, third component, which is 0, 0, and C, which is going to be on this form. So number 2 is correct. 2 is an eigenvalue, which is correct, of A. And the eigenspace associated with 2 is 0, 0, and C, which is correct. So number A is correct. As triple 1 is not an eigenvector of A, try to resolve this problem, but with alpha equal to 0. So insert alpha equal to 0 in here and resolve them. And yes, 1, 1, 1 is one of the eigenvectors. So from this definition, this is not correct because it is an eigenvector of A. It is an eigenvector, not an eigenvector. So this statement is not correct. Number D, 0 is an eigenvalue of A, already answered, with algebraic multiplicity of, with geometric multiplicity, as you can see, equal to the algebraic multiplicity of 0. Yes, exactly right. The algebraic multiplicity is 1, and the geometric multiplicity is 1, so it's correct. Okay, as I told you, A, B, and D, E are all correct. Alpha equal to 0, as we did the analysis. For number 7, he is stating that in the vector space R4, consider the vector. He is giving you U and V, and W, which is 2, 0, 3, and 1. Let F basis, which is U and V. He's giving you F, A, B, C, D belongs to R4, and such that B equal to 0, and A minus C plus D equal to 0. We want to check if this is correct or not with respect to the basis that's given. All I have to do now is to make the substitution and to check for the result. So for number A, let's make the substitution. So I will replace A by C minus D. I will put B equal to 0, so I will end up having this shape, which means that it's going to be 1, 0, 1, and 0, and the other vector is going to be -1, 0, 0, and 1. And let's compare these two vectors with what is given as U and V. So from these two vectors, this is correct because V and is a linear combination of these two vectors. This is U and V, and they are linear combination from these two vectors, so A is correct. Let us see first if it is linearly independent. Of course, they are linearly independent. I'm talking about B at the time being. In B, he's asking you if the vectors U, V, and these two additional vectors, 1, 2, 4, 4, 0, 0, and 2 is linearly independent sequence of vectors in R4. But it is not a basis of R4. So all I have to do now is to check that they are span and they are linearly independent. To check first if they are linearly independent, all I have to do is to find A1 times U, A2 times V, A3 first vector, A4 second last vector, and it should equal to 0. I should have A1, A2, A3, and A4 all of them equal to zeros to have this right. Now let us solve for A1, A2, A3, and A4 to have a unique solution, and it is the trivial one. That's all equal to zero. So all I have to do is to put the vectors, which 1, 0, 1 and 0, 0, 0, 1, 1. This is U and V. These are the two given vectors. Try to work your magic in order to discover the rank of this matrix. Second, does it span R4? يبقى إذا ده في الأول linearly independent. طيب does it span R4? Since the contains exactly 4 vectors and they are linearly independent, so it can actually is a basis for R4. Once more, so now it's linearly independent and it span all the vectors in R4, so it could work as a basis for R4. But once you start reading, he's giving you the sequence, linearly independent sequence, okay, vectors in R4, but it is not, no, it is a basis for R4. So this, once more, we face the not word, and this is for this statement is not correct. For number C, there exists a basis for R4 that includes the vectors U, V, and W. This is U, V, and W. Okay. خلينا نروح على طول. Okay. C is not correct because W is a linear combination of the other two vectors. It's very, very simple. 2, 0, 3, and 1. And we have these two vectors. I believe if you multiply the first by 2, so multiply by 2 and add them together, you will have W. This is why it's not correct. DUV equal to UVW. From this point, this is going to be correct. Because actually W is a linear combination, so it's correct. So both C and D are really very simple once you remark that W is a linear combination from U and V, and I've also wrote to you how it is a linear combination. It's 2U plus and V. The last one, W doesn't belong to F, W belongs to F. It is a linear combination of these vectors, so it's a part of this subvector space. Question number 8, AB belongs to 4 by 4, such that A has characteristic polynomial, is giving you the characteristic polynomial. So I can solve this characteristic polynomial to get the eigenvalues, which is very, very simple. And 2.000 is an eigenvector of B associated with eigenvalue of -1. So first of all, I will have to solve this problem, making the analysis by getting the eigenvalues, and then I will check for the eigenvectors. Let's do so. So the first thing that we will do now is to be sure that the matrix A is invertible, and once it is, there is a link between the invertibility and the eigenvalues. A square matrix is invertible if and only if 0 is not an eigenvalue of A. So all I have to do is to just simply get the eigenvalues and then check if 0 is one of them or not. How to get the eigenvalues? Try to analyze this equation. And this is an equation of order 4, so all I have to do is to solve it easily, which is very, very simple. So all I have to do is try it. I have x4 minus 5 of an x squared plus a 4 equal to 0. This can be put simply on these two brackets, x squared. This is 4, that's 1, the minus equal to 0. This can be easily factorized into x and x, 1 plus minus 1, and this is x minus 2 and x plus 2 and equal to 0, which is going to develop x1 equal to 1, x2 equal to -1, x3 equal to +2, and x4 equal to -2. So I have 1, -1, 2, and -2 are the eigenvalues of this characteristic equation of this matrix. So it's correct since the eigenvalues are different than 0. These are the eigenvalues lambda equal to 1, -1, 2, and -2. So mainly I can answer many questions as I remember. The matrix A is invertible, yes, doesn't contain 0. Okay, is an eigenvector of V, it's really very simple. All I have to do is to check, so it's not correct and there is not enough information on this. I don't have the main matrix in order to check if this is eigenvalue or not. Don't have enough information about this. Number C, 1 is an eigenvalue of A, but it is not an eigenvector of A power 5. This is not correct. Since 1 is an eigenvector of the eigenvalue of this problem, so it will be also an eigenvalue for A power 5. So once more we face the not comment. It seems like it's repeated in plenty of questions that you have the not or the inverse of the true statement by just inserting the not. So please do read carefully. So this is not correct. The first column of matrix B is -1 and 0. This will need an extra attention. So for number D, okay, class number C, okay? Okay, just a second. For number D, let us see. Let's see if I have 2 triple zeros here, and let's see if this is gonna work. Okay, now I have B of x equal -1 of x, and so B times 2 triple zero will equal to -1, 2, 0, 0, and 0. Now for this problem, simply remark that B times 2, 0, 0, I will make -1 times 2. And for this to be true, the first column of V must be of the form -1 and triple zero. So number D is correct. The last statement, A minus 2I4 doesn't equal to 0. This is not correct because actually this is a definition for the eigenvalue, and we have eigenvalue 2 is one of the eigenvalues from this problem, so it should equal to 0. So it's not correct as an eigenvalue. Question number 9, what I remember, it's really very simple, but let's see it. Let's E be a vector space of U1 into UR. Eliminate elements of E, so all of this are vectors of E. Under these conditions, if U1 up to UR is a linearly dependent sequence, so you have from U1 up to UR a set of linearly dependent vectors. Then for any V, for any vector V, okay, let's check that it belongs to E. So how to do so? The sequence U1 up to UR and V is also linearly dependent. So once you have from U1 to UR a linearly dependent set, so if you add another vector, it will also be a linearly dependent set. So this is correct. For any J belongs to 1 to R, we have U1 to UJ is a subset from U1 to UR, which is correct from the definition. See, some of the questions, actually you can answer them just from the definition of the slides or from reading the slides. So number A is correct as I told you from the definition. Number B also correct from the definition of the sets. Okay, number C, there exists a V belongs to E such that dimension of U1 to UR, we say dimension of U1 to V, which means that these two sets are not equal because one of them is already added. But the two sets are not equal to each other. This is completely wrong. If the dimensions are the same, it means that V is a linear combination from these two vectors, so these two bases are exactly the same. This is why this statement is not correct. E, U1 to UR, dimension of E equal to R. Then the sequence U1 to UR is linearly independent, yes, correct. For any V belongs to E, we have U1 to UR, it's a subset from this set, but it doesn't equal to 2, no. If you have V belongs to E and we have U1 till UR, okay, so it's a subset from U1 up to V without any conclusion. The dimension of the vector span, of course, it's written to you in order to make the definitions correct. Okay? This is for the last statement, okay? For question number 10, this is really very good question. This is one of the best questions in this exam. He is giving you in the vector space R4, consider the subspace F, and he's giving you its basis. Consider the vector space G, and he's giving you the conditions. And he is giving you also another vector space, which is H. So, summarizing this problem, this is the F, this is of dimension 2, this is G, which is A, B, C, D, with two conditions. Once you use these two conditions, it will make the dimension also equal to 2. And this is H, which contains 3 vectors. So, actually the dimension of H is 3. So, this is a summarization of what's above. He's asking you if the dimension of F intersection X H equal to 1. We need to check about this. In order to check that, I will use F intersection H. We actually encountered this in the dimension theory, which states that dimension F plus H equal to dimension F plus dimension H minus dimension of their intersection. Converting it like this is going to be easy for us. All I have to do now, dimension F is already known because it contains 2 vectors. Dimension H is already known, 3 vectors, linearly independent. Okay? So now I need to check for F plus H. So all I have to do now is to get the dimension of the basis of F plus H, which is simply gonna be adding the basis of F plus the basis of H. So this is gonna be F plus H, this is the F vectors, and the H vectors added all together. What's remaining to check is to be sure that these vectors are not linear combination from each other. How to do so? I will go back for our matrix. Here we go. Okay. I will need to check the dimension of F plus H. This is the first vector. This is